Hello viewers and my dear students, welcome to session 9 on thermal analysis where we are doing demo on simple 1D heat conduction problem with convective heat transfer at one end and typically known as composite wall problem. Now this is session 9 and 7 and 8 we have started this problem in session 7 itself where we concentrated on theoretical aspects of it. On 8 we have started verifying using answers and I'll tell you where exactly we were at the end of session 8. Okay, now at the end of session 8 we had modeled it, okay, and we had assigned the material properties, everything, and we have even meshed it. That means pre-processing is completely done. Please go through my session 8, you will know how exactly we have arrived at this. Okay, as you know here I have given the title here, I give it the log file name also Gurda 20. Okay, where whatever we do in graphic user interface here, that will be stored in this. Okay, this now as you know here, this there are three areas here. First area, second area and third area. First area has a thickness of 0.3. Second area has a thickness of, actually if you see here plot areas, this has a thickness of 0.3, this has 0.15, this has 0.15. Now you see here, this itself I have taken, this is 30. Okay, this is 30 elements are made, this are made 20 elements. That means in this itself, in this area itself, 30 into 20, 600 elements you'll get here only. Then actually here also, 30 here I have divided into 10 elements. Okay, under meshing 10 elements. 10 into 30, here only 30. Okay, 300. 10 into 30, 300 here. Here also 10 into 30, 300. Totally 1200 elements I have created here. Okay, see here, this is 30, this is 20 elements, 20 divisions are made here. This is 30 divisions are made. 20 divisions mean 20 elements here, 30 elements here, 600 elements here. Here 10 divisions, this is 30, okay, 300 here, 300 here, 1200 elements. Totally I have created 1200 elements. Plot elements, you see, if you see here, if you count all this element, these are all, each one is a plain 55 element. Totally 1200 elements you have. If you can even see by this, okay, list elements, if you see, okay, see here, there are so many elements created and you can see 1200 elements being created. Anyway, it's all verified. Okay, now we have come to the pre-processing stage. Now we have to go to loads. Loads, as you see here, loads, define loads, apply U plus, thermal, temperature, on lines. Here, as you know, it is subjected to 20 degrees. Just say okay, take temperature, put 20 here. Okay, put 20 here. In that way, this is subjected to 20 degrees. But as you know here, the fluid temperature is 800 degrees here. The convective heat transfer takes place from this fluid to the surface. And as you know here, this is subjected to convective film coefficients and that is convective load. That means this line is subjected to convective load. For that, what we do is, that is apply convection on lines, click on this, just say okay, and then film coefficient, how much you see, the film coefficient is 25, okay, film coefficient is 25 and bulk temperature you see, it is 800 degrees, okay, film coefficient 25, bulk temperature 800, that is, the fluid temperature is 800 and film coefficient is 25, we just feed it, okay, now it has come here, that means this fluid temperature here is 800, okay, and the convection takes place from this higher temperature to the region of lower temperature. And now, as you know here, okay, as you know here, this is the surface temperature. This surface temperature we have found out to be 304.8. It should be verified as 304.8. Then as you know, T1, T2, T3, T4 and all that to be found out. Okay, anyway, everything will do. The first thing is everything has to be verified here. This is the starting. This should be 304.8 degrees and all that. Anyway, now this we have applied the loads. Now we'll solve it. Okay, we'll now solve it. Solution. First you check whether it's a steady state analysis. Steady state analysis. Okay. Now solve. Current LS you do. Okay. Then say okay. It takes time. You have to wait. Okay. The solution is done. Message has to come. If this message does not come, you are sure that you have gone wrong somewhere in between. Now the procedure is correct and we are in the right track. And if you want to save, you can save DB here. Save and resume significance, I've told you. Save up till here, you can save it and all that. Anyway, okay, now I'll go for general post process. Okay, see here, the general post process, once you go, plot results I'll go, contour plot I'll go, DOF solution I'll go, nodal temperature if I go. Okay, this is the temperature plot. As you see here, directly here 304.762, it is here 304, and we have almost got 304.8. Okay, by theoretical calculation. Though fluid temperature is 800, convection takes place from the fluid to the surface, and here on the surface end it is 304.8 by theoretical methods. Now it is clear that it is 304.7 even by Ansys method. That means you are more or less okay. Okay, what we have done theoretically and also by Ansys is correct. We'll find out the temperatures here. We'll find out the temperatures here and all that. Before that, we'll verify this that is thermal flux also. Okay, contour plot, nodal solution, thermal flux vector sum. You see okay. Now you see this is a very good verification. 12,381 watt per meter square. This is what you had got it theoretically also. 12,380 there. Now it is 12,381 watt per meter square. That is, this is the amount of heat being conducted or heat lost to the surroundings. That is the amount of watt per, so much of heat per watt per meter square is the heat which is flowing through the composite wall and finally escaping into the atmosphere. That is heat lost to the surrounding is 12,381. Okay, this is the thing what I've said. Okay, now you see here, this, now I'll redo this. See here, contour plot, nodal solution, DOF solution, nodal temperature, you say okay, okay. Now this you got, okay. Now you see here, this is TS or T1, that is 304.762, you already know. We want to see a T2 and T3, T4 is this or T0, this is 20 degree. This is, he clearly says blue is 20, this is 20. But at least this and this have to be verified now. For that, what I'll do now, plot controls, numbering, node numbers on you just do. Once you do node numbers on, okay, you just enlarge the area. At least to some extent, we'll enlarge the area on this line. If you enlarge the area on this line, okay, on this line, see here, 35, 36, 37 and all that, these are all in this line. Okay, 35, 36, 37, if you list results and nodal solution, if you go, DOA solution, nodal temperature, okay, if you say 35, 36, 37 and all that, that should have 119.1. That is T2. Correct, no? This is T2, 35, 36, 37 and all that, that should be T2. You just see here, 35, 119, correct, no? 35 you see 119, 36, 119, 37, 119. That means anywhere on this line, whatever node numbers you have, you keep enlarging and see on this line, throughout on this line, it is the interface between the first material and the second material. Throughout, you see the node numbers and see here the list solutions. You will have same 119.1. Okay. Now, let it be there. Now, what I'll do, I'll fix this. Okay. In the same way, you just see. In the T3 region also, we'll just see. Zoom model, if see, this is T3, no? 676, 677, 678 and all that. These should refer to T3, okay, T3 and should measure 57.2. Okay, immediately list results, nodal solution, nodal temperature, okay, see, and fast you do. Okay, 676, 674, 675, 676 and all that. Okay, 674, 675, 676 and all that. Okay. 674 you see. 57 point something. What you got? Almost correct. 675. 675, 57.143. 676, 57. In that way, what we are doing is correct. That means we have clearly verified. I'll remove this numbering, plot controls numbering, this node numbers off I'll do. Okay. Now you see here, this how to find interface temperatures using Ansys, I have told you. Okay. And at the same time you'll see here, before you forget, plot results, contour plot, nodal solution, first nodal temperature, this temperature plot, no, without forgetting this write meta file, invert white and black you do, you get it in the paint, you save that as a temperature plot. Okay, this you save it on desktop and show it to the examiner. In the same way, one is this temperature plot. Another, as you know, nodal solution, thermal flux vector sum. This is another very important thing. 123819, what you have verified. This also you take the printout, that is plot controls, write meta file, invert white and black and call it as thermal flux plot, that also you show. And after this, you take the vector plot predefined. Okay, thermal flux vector plot. If you say this is also a beautiful thing you see here. This is starting 12381 is watt per meter square, is the quantity of rate of heat flowing through the composite wall. Okay, and it is escaping to the atmosphere also. This is called heat loss to the surrounding. How much heat loss to the surrounding is, as you clearly see, so much 12381 watt per meter square of heat is being wasted or being escaped to the atmosphere. Okay, this is another thing under plot controls, meta files. This also you take. Okay, after this, after this you see that plot elements you do. You have got all this. Then finally, this element table path operation, define path by nodes. Take this and this you take. Okay, and call it as some name. Okay, and those. Then map onto path you say, and what you want is temperature, no? Temperature you have it, and plot path item on graph you see, and temperature you take. In that way, beautifully, 0.3 totally, this x-axis is 0.6. Can you follow? X-axis is 0.6 and it is from 304 surface temperature, that is at T1. T1 to T4, T4 it is 20 degree only. Okay, at 0.3, if you see 0.3 at this temperature, it is 304.8, it is almost correct. That is 119.1 at 0.3, 119.1, it is in that way it is correct. And even at this point also, it is 57.2, that is also correct. In that way, this also, you have the graphs printed, okay, under meta file and do that. Now we have come to the end of session 9. We have completed this problem. Please go through. Thank you very much friends for watching. Thank you very much.